Is it going? It's going. All right, so yesterday we learned about kinetic energy. And basically, let's do, in a couple of words, kinetic energy was energy of motion, right? So the more velocity or angular velocity that an object had, the more kinetic energy it had, right? Okay? Now, today we need to learn about what is called potential energy. So yesterday you guys had kind of a basic understanding of what kinetic energy is. Any idea what potential energy is?
Stored energy.
Yeah, it's stored energy. It's energy that has the potential to become kinetic. Okay? So potential energy is exactly that. It is stored energy. All right? So we're going to use the generic symbol PE to stand for potential energy. All right? And as you guys just said, potential energy is energy that an object has stored or saved. All right? So we will see as we go through this that a good way to kind of check if something has potential energy is to ask yourself, can this stored energy be converted into kinetic energy? So we'll talk about that a little bit more later on. All right. So today I'm going to talk about 4 different types of potential energy, but we're only going to learn equations for 2 of them. Okay. The other 2 are just going to be kind of talked about in the sort of nebulous, concept-y realm. Which will be important when we get to some kind of big picture concept-y ideas, but in terms of problem solving, they're not going to be as important. So let me talk about the 2 sort of nebulous concept-y ones first. All right, and I'll be honest, you guys, some of these terms are terms that I've used with my regular physics class. They're probably a little bit oversimplified, and you could probably take some issue with the distinction here. But here's the idea then. So you can store energy in a battery, right? Okay. So we are, for the purposes of this class, going to call that electric potential energy. Okay. I'm going to use the symbol ZPE for that. Z stands for zap. Okay. You'll see in a minute why I didn't use an E. But all right. So electric potential energy is energy that's stored in something like a battery or some other sort of power source. So examples would be, like I said, a battery. If you rub a balloon on your hair, you store up energy in your the charge on the balloon or in your hair. So those are other forms of energy. Okay. Another form of potential energy we're going to call chemical potential energy. All right. This is basically energy that is released by burning it. Right. So gasoline, you burn gasoline to make a car go. This morning you had some Cocoa Puffs for breakfast. You burn those Cocoa Puffs, give yourself kinetic energy and brain energy and whatever, right? Cool? All right, so those are 2 forms of potential energy. And in both cases, you can take, energy from a battery, energy from gas, energy from food, and convert that to kinetic energy. Okay? So these guys, we're really not going to do any calculations with these, but I want you to understand that they are, technically speaking, forms of energy. Okay? Cool? All right, a quick comment about this chemical potential energy thing here. So when you eat, if you eat Cocoa Puffs, on the box it'll tell you how many calories are in that. Okay, you can literally convert in the same way that you can convert from meters to feet, you can convert from calories to joules. Okay, so if you eat, I'm terrible with nutrition stuff, but if you eat, what are you supposed to eat, 2,000 calories in a day? Yep. Right, you could convert that to some number of joules, and basically if you eat 2,000 calories, if you converted that to joules, that would be equivalent to sort of how much energy you gain from your food. Cool? And you could then convert that to kinetic energy or, energy to run your brain or lungs or whatever. Cool? All right. So any problems with electric potential energy or chemical potential energy? All right. So the reason I used ZPE for electric potential energy is because EPE we are going to reserve for elastic potential energy. Okay. Now again, this notation is mine. Like if you look in physics books, most of them won't use EPE and EPE and all this stuff. But I've found it to be helpful to distinguish between them. So, all right. So elastic potential energy is energy that an object has stored because it is either stretched or smooshed. Okay. Smooshed, obviously not being a technical term. All right. And a minute ago, I had a rubber band. Where did I put that rubber band?
That rubber band.
Oh no, I'm gonna find my rubber band.
It's on the ground.
It's probably on the ground at the screen. Ooh, you have my rubber band. Oh, that's right. I tried it somebody's second hour. Whoa. In a non-aggressive act. He didn't even notice, to be honest, because he was listening to his headphones. All right. Anyway, so look, this right now, well, basically has no energy, right? Okay. In a minute, we'll learn that's not exactly right, but I can definitely store energy by stretching, right? Okay, so right now it would be accurate to say that this has elastic potential energy. How can I prove that it has elastic potential energy? If I let go of it, that elastic potential energy gets converted to kinetic energy. Cool? All right. So examples of things that might have elastic potential energy would be a stretched rubber band or slinky, a spring. Sometimes springs can be squished instead of stretched, right? So you could smoosh a spring and store energy that way. When you blow up a balloon, the balloon stretches and stores energy, right? Then if you don't tie it off and you let it out, that elastic potential energy pushes the air, right? And in return, the air pushes the balloon and the balloon goes shooting through the air, right? Okay. I don't have one anymore, but I used to have a Nerf gun laying around. You know, when you load a Nerf gun, you're squishing a spring in there, right? And then when you pull the trigger, it uncompresses and, you know, converts the potential energy from the spring to kinetic energy of the Nerf gun. Cool? All right, so we actually need to learn how to calculate elastic potential energy. All right, and in order to do that, we need to learn what is called Hooke's law. All right, so this actually is something that we probably could have covered when we did forces, but it always fits in better in this energy chapter. All right, so a simple spring, I guess technically, the technical term for this would be an ideal spring. But in this class, we're going to always assume that all of our springs are quote-unquote ideal. All right? And they follow what is called Hooke's law. All right? So here's what Hooke's law says. Hooke's law says the force exerted by a spring, or on a spring, right? Because if you push something, if you pull a spring with X amount of force, then it's pulling you with that same force, right? Okay? So the force exerted by a spring is always going to be equal to some constant, K. I'll talk about what that constant means in a second. It's called the spring constant. We're going to write that. Spring constant is what K is. Okay? And then X is the distance that the spring is either stretched or smooshed. Cool? All right. So what is K? So K is what's called the spring constant. And basically what it does is it measures the amount of force required to stretch or smoosh the spring a certain distance. Okay? The higher the spring constant is, the stiffer the spring is. All right? So before we talk about this elastic potential energy equation, let me talk for a minute about this equation. All right? So I think hopefully in the notes I gave you a blank. Oh, yeah. All right. So I got the spring set here. Okay? So I kind of quickly set this up. So right now it's set so that right now the spring is stretched 0 meters, right? In other words, it's relaxed. There's no force acting on it other than its own weight. And so it's not stretched, right? Okay, so what I'm going to do is I'm going to apply a force to this spring, and we're going to see how much it stretches. Follow? All right. For simplicity's sake, I'm going to, just for this one time only, I'm going to use an acceleration of gravity of 10 just to make the math a little bit quicker. Okay. Follow? All right. So what I'm going to do is I'm going to hang 200 grams from it. So 200 grams is 0.2 kilograms. Cool. So 0.2 times 9.8, 0.2 times 10 is going to be 20 newtons. So this is, no, it's 2 newtons, sorry. 2 newtons worth of force. Follow? All right, so I'm going to put 2 newtons of force on the end of the spring. If I can hold 2 newtons, and let's see how far it's stretched. It looks to me like that's about 4 centimeters. Okay, so here's what I just discovered. I discovered that when I applied a force of 2 newtons, it stretched 0.0, what did it say, 4 centimeters, so 0.04 meters. Cool? All right, so what Hooke's law is telling us is that the force is proportional to the amount that you stretch it. So if I double my force, hopefully the amount that it stretches should double. Okay, so let's see if it works. So I just did 2 newtons. Let's double the force. So all I'm doing is just adding another 200 grams on there. And now it is stretched, if you measure to the bottom of the spring when it stops bouncing, basically 8 centimeters. Okay? So when I put 4 newtons worth of force on here, it's stretched 0.08 meters. So if you had to guess, what do you think 5 newtons would get me? Yeah, I think 0.1, right? It looks like every 1 newton stretches at 0.02, right? So let's try it. So here's 5 third grams, which is about the same as 5 newtons. And it stretches it to the 10 centimeter mark. Cool. So 0.10. And therefore, what if I put 10 newtons on it? How far should it stretch?
0.2.
0.2, right? Double the force would be double the stretch, right? So let's replace the 500 with 1,000. And you can see it stretches pretty much to 0.2. Cool. All right, so check it out. Hooke's law tells us that F is equal to K times X, right? So if I rearrangeify this thing, I get K equals F over X, right? So let's take a second for each of our trials that we just did. Let's figure out what K is. Okay. So I'm just going to, for each of these, I'm going to do force divided by X. Follow? So that requires a calculator because I'm a little sleep-addled today. Yeah, is that a word? Sleep-addled? Is that a thing? Lack of sleep-addled? All right, so anyway, for each of these, so if I do 2 divided by 0.04, it gives me 50. What are the units going to be there? Newtons per meter, right? Because I took my force and divided it by my x. I took the number of newtons and divided it by the number of meters. Newtons per meter. So this is telling me how many newtons I need to stretch at 1 meter. 50. If you repeat the process here, what should I get? What's 4 divided by 0.08? 50. What's 5 divided by 0.1? 50. What's 10 divided by 0.2? 50. Okay? So K is called a spring constant because it's constant, right? Follow? All right? So often problems will be set up where I'll say to you, you know, Roy stretches a slingshot back and he exerts a force of something to stretch it this far. All right? And what you'll have to do then is find your spring constant by using this equation. Follow? Questions about that? All right, so once you've got your spring constant, I'm going to jump back a page if everybody's okay with that. Everybody all caught up with what we've done here? Once you've got your spring constant, you can then use that spring constant to calculate your elastic potential energy. So your elastic potential energy is 1/2 kx squared, where k is still that same spring constant. Follow? So let's go back to our chart and calculate our elastic potential energies. All right? And also worth noting, when it's not stretched, what's x here, you guys? Maybe I should rewind. What does x represent? The distance it stretches from its relaxed point. So right now, x is 0. So when you measure your x, you're measuring from here. Does that make sense? So right now, x is 0, right? So what's the elastic potential energy right now? 0. Why? Because it's not stretched. The only way that it would have elastic potential energy is if it was somehow stored by the spring being stretched. Follow? Questions? All right, now notice in the equation, I don't know if you guys noticed, 1/2 mv squared. This is very similar to the kinetic energy equation, right? Except it's k and x instead of m and v. All right. But we can certainly go through, and for each of the x's, we can figure out how much kinetic energy, or how much elastic potential energy this has, right? So let's do that. We're going to add one last column. EPE equals 1/2 kx squared. So let's go through and calculate each of these. It's basically just kind of plug and chug, which I could do if I had not sat my calculator down somewhere dumb. All right, so do you think this is going to be, like, this is linear, right? As my force increased, so did my x, right? What do you think is going to happen over here? Is it going to increase by the same amount each time, kind of? In other words, if I double how far I've stretched it, am I going to be doubling the elastic potential energy? No, because of the x squared, right? Okay, so let's see. We know our x, we know our k, so we can find our EPE. So let's see. So for the first one, we're going to have 25 times 0.04 squared. So that gives you 0.04 joules. The next one is going to give you 0.16 joules. I don't know if there's really that much educational value to doing this, but I guess we might as well finish this from this part. 25 times 1 squared is 0.25 joules, and that once more gives you 1 joule. Cool? All right, so I don't know that there's a ton of point in doing this, but let me just point out real quick that if you were to graph this, it's a parabola because of the x squared. Cool? All right, any problems with elastic potential energy? All right, so we should probably do an example. I think did I write one up? I didn't. Yeah, I was going to do that spring example and stop there, but we should probably do an example. Oh wait, no, we can't because we haven't done conservation of energy yet. So I'm totally ahead of myself.
Are we done?
So, well, we're done with elastic potential energy. Everybody good with that? All right, and then the GPE notes are even quicker. So,
Really?
yeah, totally. Questions with elastic potential energy? All right. And I guess I should probably point out that certainly there's no reason why, for example, if I gave you EPE and K, you could find X, right? Just by using some algebra. That is the goal, yes. All right, so finally, fourth type of potential energy we're going to talk about is called gravitational potential energy. All right, so an object has gravitational potential energy because of some elevated position. Okay, now this is a little bit dodgy here. So the equation for gravitational potential energy is this. It's mass times acceleration of gravity times height. Okay, so when I talk about the height of an object, I'm not talking about, oh, Mr. Hecker is 5'10", so the height is 5'10". No, the height is sort of how far the object is elevated. Okay, so if I take the duck and hold the duck up, then to calculate the GPE, I would take the mass of the duck, multiply it by the acceleration of gravity, and then multiply it by the height from the floor up. Good? All right. So, a couple things about this. So, first of all, when you do this, we sort of all need to agree on where we're measuring our height from. Okay? Because it turns out that it's sort of relative. It depends on how you measure your height. Right? Like if you're standing at the edge of the Grand Canyon, you measure your height from the top or the bottom of the canyon, right? All right, what I will always do in my problem solving is I will find the lowest point in the problem and call that a height of 0. Okay, so if I know that the person's going to fall into the Grand Canyon, then I will choose the bottom of the canyon as a height of 0. Make sense? Okay. The one other thing that I should comment on here is, technically speaking, the acceleration of gravity is negative 9.8, right? Okay. For this equation and this equation only, when we use the acceleration of gravity, we're going to use positive 9.8 meters a second squared. All right? And the rationale behind that is basically this. If I hold the duck up in the air 2 meters, then his downward acceleration, if I was to release him, would be negative 9.8. and he's got the potential to move down 2 meters. So technically speaking, both of these numbers are negative. Okay, your acceleration of gravity is negative, and the height is negative because there's the potential to move down that distance. Make sense? All right, so it's just sort of understood. You use positive network. Good? Questions? Okay. Okay, so I guess that's it. So examples of things that have gravitational potential energy: a painter at the top of the ladder, skydiver, he's not on the ground, skier at the top of the hill. Notice you don't have to be off of the ground to have gravitational potential energy, right? If you're at the top of the hill, then you have the potential to go down the hill. Okay? So again, you measure your height vertically from the lowest point, so from the bottom of the hill. Okay? So why does it have potential energy? I knew I was missing something here. So why does the duck have potential energy? Yes, because there's a force on it. How did I prove that the rubber band had potential energy?
When you release it, it moves.
When I released it, it moved, right? Because the rubber band's sort of internal force gets converted to motion, and it now has kinetic energy, right? Similarly, if I hold the duck up in the air, what happens if I release it? He's going to move, right? Almost as though it was attached to a rubber band pulling it down to the earth, right? Does that make sense? All right, so in the same way that a stretched rubber band can convert that potential energy to kinetic energy, when you pull something away from the earth, you're stretching a rubber band as you pull it away from the earth, right? And then when you release it, you're allowing gravity to pull it down and convert that energy back into kinetic energy. Follow? All right. So any object that's, I think this is all pretty straightforward stuff. Oh, here was what I was saying before. I knew that I'd written that in there somewhere. Notice your GPE is going to depend on your coordinate system. So in other words, where you choose your height of 0 is going to be important, right? Again, I will always choose the lowest point in the problem to be a height of 0. If you choose something different, you'll get a different value for the GPE, but usually calculating the GPE is just a means to calculate something else. And regardless of where you pick your h equals 0, you'll get the same answer at the end of the problem. Okay? So you'll see what I mean after we get to the next couple sections. So it shouldn't be an issue up until then. All right, questions? All right, so let's just do a couple quick examples. We're back to Carl the cat and Dave the dog. I'm going to kind of plow through these because they're pretty straightforward. So here we go. So for Carl the cat, his mass is 3 kilograms. Basically, I just want to talk about units here. Which I didn't do with my elastic potential energy example. Darn it. Well, if you check the units, the elastic potential energy units do work out to be joules. You can go back and do the calculations if you want. Go, brain. All right, so Carl has a mass of 3 kilograms. He's sitting on a balcony 4 meters high watching the stars. So the height is 4 meters. We're going to calculate his GPE. So that's mass times acceleration of gravity times height. So his mass is 3 kilograms. The acceleration of gravity is 9.8 meters a second squared. Remember to leave it positive. Times the height, which is 4 meters. Again, technically speaking, these are both negative, and the negatives cancel. We don't worry about it. Okay. So multiply that out. What do we get? 12 times 9.8 is 117.6. And the units do work out to be joules, because you get kilograms, meters squared, per second squared. So it does work out as joules. Good? All right. Dave's got twice as... Oh, question?
Well, that's just like a side note.
Yeah.
Is that equation sort of like the work equation?
It's very...
It is the work equation.
Yeah. How do you know the work equation? Have I taught you guys the work equation yet?
Chemistry.
Oh, I gotcha. FB, is that what you're talking about? Gotcha. Yeah, exactly. Because the MAG is the force of gravity, and the height is the distance. Yeah. I didn't know you guys had learned that. Very good. Okay, all right. Everybody good with Carl? All right, Dave's got double the mass, so what's going to happen to his GPE?
But I have a question.
Oh, yeah, shoot, sorry.
You say that we're doing passive then?
Yeah, so ignore the red.
Oh, right.
The red, as I wrote the red, what I said was, technically speaking, the 9.8 is negative and the 4 meters is negative, but the negatives cancel, so we just sort of ignore them.
Okay.
Good? All right, everybody good? Evan, you doing okay with that? Whoa, I know. All right, so what's going to happen? Dave's got twice the mass. What's going to happen to his GPE, guys? If you double the mass, you're going to double the GPE, right? So I'm just going to, what is that time to get to double it? 235.2. Oh, not newtons though, sorry. Joules. Cool? And you can definitely go through and calculate that. All right, so once again, as was the case yesterday, Carl is jealous. So to compensate, because Dave's got more energy, so Carl climbs up to a balcony that's twice as high. What's going to happen? If you double the height, what should happen to your GPE? Double it, right? So today it worked. Yesterday it didn't because of the squared in our velocity equation. Everybody good? All right, and then one last thing. And I think, yeah. Oh, gotcha. Last calculation and then a quick comment. All right. We can work backwards. So I give you the GPE, we can find the height. Please be careful. There's a super common mistake that people make in their calculators here. It's a dumb mistake, but I see people make it all the time. So here, warning. Danger Will Robinson. All right, here we go. So let's see. Dave. So here's what we know about Dave the dog. He's got a mass of 6 kilograms. He's got a GPE of 300 joules. We're trying to find the height, right? So obviously you guys can go through and do the calculations. It's not, rocket science. So here we go. So GPE is mass times acceleration of gravity times height. So if I rearrange this, I get height is GPE over MAG, right? Please be careful putting this in your calculator, because what you're going to get is you're going to get 300 joules divided by 6 times 9.8 meters a second squared. So everybody type that in your calculator. Tell me what you get. Yes?
What's that?
Lost in space, I think? I said that, and I don't even know where that came from. How that entered my head. Yeah, it's an old, 60s sci-fi show. And don't quote me on the decade, because I could very well be wrong.
I just remember hearing it somewhere else.
I think they remade a movie of it in, the 90s with... Who's the dude from Friends?
Jimmy Short.
No, Joey.
LeBlanc.
No, Matt LeBlanc. Good, yeah. I think he was in the movie. But I might be mixing up my old weird sci-fi shows. Okay, so has anybody typed this in their calculator?
Yes.
Did anybody get 490? Good. All right. What always happens is people type this in and they type this into their calculator. They go 300 divided by 6 times 9.8. And that's not right.
Oh, you're right.
Okay, I want 300 divided by 6 times 9.8. Follow? So please be careful on that. So if you do it, it gives you, what's 50 divided by 9.8?
5.1.
5.1, thanks. Cool? All right, last thing. I don't even think we need to write anything else to do this last slide. Please notice, this is huge, you guys. An object can have more than one type of energy at a time. Where did that rubber band go? I launched it, lost it. Uh-oh.
Why do you have a jar
I don't know. All right, so pretend this is a stretched rubber band. All right. It's embarrassing.
It's under your desk over there.
Is it?
It's like this way.
It's under the, it's by the power strip.
Aha, thank you. All right. Okay, so right now, this has 3 different types of energy. What types of energy does the rubber band have right now? What kind of potential? It's got elastic potential energy because it's stretched. It's got gravitational potential energy because I'm holding it way up high in the air. And it's got kinetic energy, right? Now what kind of energy does it have?
Rotation.
It's got rotational, right? Follow? So, an object's gravitational potential energy just depends on the height. It's got gravitational potential energy. Okay? An object's kinetic energy just depends on the velocity. Follow?
Yeah.
So don't assume that, oh, it's got kinetic energy. It doesn't have gravitational. That's not true. Okay? You can have more than one type of energy at a time. All right? So very often we will talk about total energy, which is all of the different types of energy added up at one moment. All right? And then occasionally we'll talk about mechanical energy, which basically is all the types of energy except for electric and chemical. Okay? Cool? Questions? Okie dokie. So, due tomorrow. 8.1a is due tomorrow. 8.1b is due on whatever the day after tomorrow is. That would be called Thursday by most of us.